So conservative forces like gravity, spring, and electromagnetics, not friction, not heat engines. They're not conservative. A Carnot cycle, an ideal Carnot cycle is conservative, by the way, but that presumes zero entropy, which is unrealistic. So the idea is the work is the same between points A and B no matter what the path. The work to get to the top of the hill doesn't matter which way you go. If you go up Everest from the South Col versus the northeast route, it's the same amount of work either way, although the northeast route is much more dangerous. So if you go in a closed loop path, if you return to the start, the work done, the total work done, returning to the start, starting from the start, going some path, doesn't matter the path, back to the start, the work done is zero. It's a function of the starting and ending points only. Gravity is an example of that. So gravity is a function of weight times the change in y. That's it. The work done, W dy, negative WH, if you just lift it straight up, WH. If you go this way, if you integrate and you do dr cosine theta and you do all those integrals, you get negative WH if you integrate it all. Just like if you go straight up. Work is negative. Work is being done by the weight, so the displacement's up, the weight is down. There we go. Displacement up, there's the displacement, weight is down. Oh, get real, you silly machine. There we go. There's my pointer. Come on. Get out of it. Turn off the laser pointer. I want to go to the next slide. Now, springs. Let's talk about springs. The force is negative Ks. So the total work is negative K between S1 and S2 ds, and I have 0 here, which is a mistake, which I'll get rid of. Negative 1/2 K final state, right there, minus initial state. That's the change. That's the work done. Let's look at potential energy. The idea of potential energy is storage. Okay, here's the idea here. Gravitational and potential energies add. So the work going from Q1 to Q2 going up, VQ1 minus VQ2. It's negative. If the final is greater than the starting point, then the work is negative. Notice that. The potential energy goes up, but the work goes down, or the work is negative. So this is the spring. Spring is always positive, 1/2 kx squared. Here's the negative Wy and the example. The datum is, you'll notice the datum is y is positive going down, which is a little weird. Usually you consider y as positive going up. So the potential energy going from state 1 to state 2, from y1 to y2, or the work done, excuse me, is negative W y1 minus y2. So that's a negative negative. Y1 is less than Y2 times a negative negative, so it makes it a positive. And then the spring force, the spring potential energy, 1/2 K Y1 squared minus 1/2 K Y2 squared. So the work is done by the weight on the system. So the weight is going down, you're pushing the weight up, and so you get a negative work, but you get a positive change in potential energy, which is expressed by this equation right here. Okay. At equilibrium, delta equals 0, therefore delta V equals 0. We can write that as a derivative of dV dq equals 0. Q is some coordinate, like x or y or theta. So from the previous slide, dV dq. Now, V equals negative Wy. Normally, you'd see a Wy, where y is positive going up. In this case, y is positive going down, which is why we have the negative sign here. And potential energy of a spring is 1/2 ky squared, so the derivative is just ky. Equilibrium, W over K below the datum. So, if you did it the way I prefer, up is positive y, the result becomes equilibrium equals negative W over K, which would mean below the datum, just like before. So the result is the same. It's just the way of thinking about it. The conventions. Setting up is the most difficult. So, using what you understand is what you need to do. Don't worry about what the book says, what I say, everything else. Do it in a way you understand. Same results using force equilibrium, but this illustrates the methods. And some problems are very difficult using force equilibrium.